Okay, so I'm going to do something which is perhaps a teensy bit lame, because it's bad to recycle. But as I mentioned before, I gave a mini course earlier this term at Fudan University where I talked about NSOP1 in some depth. And of course there, I talked about NSOP1 for 2.5 hours for each week for 6 weeks. So we did everything that one can do in NSOP1 over models, basically. And we're not going to do that here. But I did go through a lot of effort to like draw very nice pictures when I was talking about a certain kind of tree that you talk about when you do the proof of symmetry in NSOP1. And it seemed like ridiculous to try and do it on the fly extemporaneously when I was giving this lecture. So what I'm going to do is I'm going to just use the notes so that we can refer to the pictures and the things that were written there, because I think that that'll be clearest. But of course, the lecture itself will be quite different. So I will pull that up and we'll get started. Okay, so we had, this is the title page. So anyway, the point is to prove symmetry. So what did we do last time? Last time we proved what did we prove? We proved Kim's lemma for Kim divided. We proved that characterizes NSOP1 theories, and that has many nice consequences. For example, Kim 14 equals Kim dividing in NSOP1 theories by copying the same proof that we've done many times. And now we're going to see that in NSOP1 theories, Kim independence is symmetric. And the proof of symmetry will involve something that sometimes is called the NSOP1 tree induction or the tree induction. And this is maybe one of 2 or 3 arguments that form the core of the theory. If you understand this argument, then you can understand how to tweak it to prove most of the things that we know how to prove in NSOP1 theories. So this is going to be sort of like the one thing that we do in NSOP1 theories that really, I don't know, it's really sort of paradigmatic of how the arguments go. So what's funny is that the induction involves a weird class of trees, a certain class of ill-founded trees, which seem hard to motivate, but then you see that they somehow naturally arise from a certain process that you'd like to induct on. So we'll just dive in. So we have this distinguished class of trees. So I'm just going to fix notation to start, where in L alpha is going to be my notation for the non-limit ordinals of alpha. So if there are any set theorists in the audience that know better notation for this, I would be very happy to know. I think in the first paper where I wrote about this, we just wrote alpha minus limit alpha. But I'm going to, for these purposes, write in L alpha for the non-limits. So the elements of in L alpha are 0 and the successors inside of alpha. All right, so script T alpha will be the following tree. So you look at functions which go from beta to alpha, excluding alpha. They go from that in segment of alpha to omega. And that has finite support. So what does it mean for that function to have finite support? I mean that the number of places that it is not 0 is finite. Okay, so we see a few things. The elements of the tree are functions defined on in segments of alpha. So that's the first thing. The second thing is that these functions have domain starting at a non-limit of alpha plus 1. Okay, why alpha plus 1, not alpha? Well, if alpha is a successor, then I want the empty function to be one of the possible functions. So if I have alpha here, like closed bracket alpha, alpha round bracket, by that I mean the empty set, right? Like I exclude alpha from these intervals. So if alpha is a successor, then that's a perfectly well-defined thing I can plug in, and I will get the empty function. However, if alpha is a limit, then alpha is not an element of the non-limits of alpha plus 1. And that means that it's not permissible as a starting point of my function. So the empty function is not an element of my tree. So, if this alpha plus 1 is confusing, you could instead say beta in alpha plus 1 or the empty set if alpha is a successor. But this is a uniform way of saying it. So you only allow the empty function if alpha is a successor, and if alpha is a limit, then you exclude the empty function as one of the elements of your tree. Okay, so you have these functions defined in segments that begin at non-limits and have finite support. That's the tree. Okay, so it's not so difficult to understand how to do that as a tree. You just view the elements of the tree, so you just have the inclusion of functions as the tree partial order. So eta is below nu in the tree partial order if whenever I restrict nu to the domain of eta, I get eta. Or set theoretically, if you identify eta and nu with their graph, this says that eta is a subset of nu. So okay, this gives us a tree. Now, let's just ask ourselves the question, what these trees look like when we plug in sort of familiar numbers. So okay, what is T0? Well, T0, those are functions which are valued in omega defined on an in segment of the empty set. Okay, so how many such functions are there? Well, there's only the empty function, so you have a single function. Good, so that's a single point. Now, what happens if you look at T1? Well, if you look at T1, you have functions which are defined on an in segment of the ordinal 1, meaning that are defined either on the whole set or on the empty subset. So if you're defined in the whole set, then you have countably many options for where to send it, because you can send it to any natural number. So where do you send 0? You can send it to 0 or to 1 or to 2 or to 3. So that gives you infinitely many things, which are like nodes in the tree. And all of those things, of course, contain the empty function, which is like the root node. So if you look at T1, the omega valued functions on in segments of the ordinal 1, that gives you omega to the less than or equal to 1. Okay, and then we do the same thing on T2. So what are functions defined on an in segment of 2? They could either be defined on the set 0, 1, they could be defined on the set that only contains 1, or they could be defined on the empty set. And those give you omega to the less than or equal to 2. So it looks like we have just described omega to the n in a fancy, or omega to the less than or equal to n in a fancy way. And in fact, we have. But you see that at infinite ordinals, the situation changes. So if you pass to T omega now, notice that if I look at the identically 0 function, which is defined on the interval from n to omega, as n increases, I'm going farther down in the tree. I'm defining smaller functions. So I have the function defined on all of omega, and then the function defined on the in segment starting at 1, and then the function defined on the in segment starting at 2, and so on and so forth. Those are going down in the tree, and that's an infinite descending sequence. So that tells me that at infinite ordinals, I get ill-founded trees. I have trees that have infinite descending sequences with respect to the tree partial order. And that's what's different about defining it on in segments rather than on, say, initial segments. I can't, if I had initial segments, then I would never have these infinite descending sequences. Okay, so that is how these trees work. So when you have something infinite as your index for the tree, you get something genuinely different. Okay, now there's a lot of notation that one can introduce. So the first one is the canonical inclusion. So if I have T alpha and T beta, where alpha is less than beta, then I can think about how T alpha sits inside of T beta. And I'm going to define a function which gives me a kind of like canonical inclusion of T alpha into T beta, which identifies T alpha with some chunk of T beta. What is the chunk going to be? Well, I'm going to define a function iota sub alpha beta, which is given here. And what do I do? Well, I take a function, eta, and I'm going to think about eta as its graph. So think about it as a set of ordered pairs. Then I know that eta is defined on an in-segment of alpha, and I want to define it on an in-segment of beta. And I want to do that in such a way that it still has finite support. So there's sort of like one natural choice, which is I just extend it to the bigger the bigger in-segment by making all the new values 0. So set theoretically, that's like adding a pair gamma comma 0 for every gamma which is in the new domain, i.e. every gamma which is in beta but not in alpha. So I just take the old function, and to define it on an in-segment of a bigger ordinal, I just make it 0 on all the new stuff. And that gives me this inclusion. And you can see sort of this picture here. If I have T1, which I've indicated in blue, then I can sort of view it as the cone above 0 inside of T2. And likewise, I can see T2 as the cone above 0 in T3, and so on and so forth. So they all sort of fit together along the all zeros path. And these things compose in the obvious way. So if I extend from alpha to beta by adding zeros, and I extend from beta to gamma by adding zeros, then that's the same as extending from alpha to gamma by adding zeros. So that means that the canonical inclusion from alpha to beta post-composed with the canonical inclusion from beta to gamma is the same thing as the canonical inclusion from alpha to gamma. And these things fit together to tell me that I can view any one of these T deltas indexed by a limit ordinal delta as somehow the direct limit of the trees indexed at lower ordinals. So how can I do that? I mean, what does it mean to take a direct limit? Normally you'd like to take a union, but the functions don't have the right domain. But if I just sort of extend them to delta, then it really is the union. And you sort of see this picture here, right? So T0 is like omega to the 0. T1 is like omega to the less than or equal to 1. T2 is like omega to the less than or equal to 2, so on and so forth. How do I think about T omega? Well, I think about it as the union of these trees, where I view them as sitting together in the right way, right? Like if like T0 is sort of sitting here, and T1 is sort of sitting here, and T2 is sort of sitting here, and T3 is sort of sitting here. And because my tree has finite support, I know that everything in my tree T omega will be eventually constantly 0. And that means that if I have some node in the tree, then all of its non-zero stuff will be contained in the image of one of these trees Tn for something below. So that's for T omega. But in general, if I take any node of T delta for delta limit, then I know that there has to be some place where I no longer have non-zero values. So I can view it as the extension by adding zeros of some node in T alpha for some smaller alpha. And that says exactly that the limit ordinal trees are the direct limit of the earlier index trees along these canonical inclusions. So, this isn't deep, but it's good to fix the notation. So iota alpha beta is my name for this inclusion that takes T alpha into T beta. All right. Now, I've already used this language a few times, but it's good to fix notation for it. We have the all zeros path, which is the path consisting of functions in my tree, which are identically 0. So zeta beta will be the function in T alpha whose domain is beta alpha, the interval from beta to alpha excluding alpha, but which always takes on the value 0. So of course those things form a path, because if those things are all comparable to one another. But as beta increases, I'm going down the tree. So this is what's a bit strange. I have a path which is indexed by something well ordered, but it goes in somehow the opposite direction than you expect. As the index increases, I'm going farther down in the tree. So the index denotes the beginning of the initial segment, not the end point. So that's why these things are confusing. So if you have ever worked with trees, then you develop certain intuitions about how trees go, and somehow this mixes and matches your expectations for when things go up and when things go down, and it makes it complicated. But anyway, I mean, that's the all zeros path, goes down, and it's defined like you expect. So zeta beta is just my name for these things. Then we have concatenation, which is, I mean, we're never going to do it for anything other than adding a single node. I mean, a single new value to a node. So I can add it on top or I can add it on bottom. And how can I do that? Well, suppose that I have some node in T alpha, which starts at a successor ordinal. So it starts at T beta plus 1. Then I'm just going to define eta concatenated with alpha as saying, well, I'm going to extend by defining the next value, I mean the value at beta now, to be I. So eta concatenated with I now has the domain beta to alpha. So I've sort of removed one from, I've added a new element onto the domain. So I've extended my initial segment by one element, or my in segment by one element, and then I've defined it on that new element to be I. Now, you might notice that this could create problems, because one of the conditions of being in the tree was that the initial segment begins at a non-limit. So beta could be a limit. I mean, of course, beta plus 1 is a non-limit, but beta itself could be a limit, right? I mean, it could be like omega plus 1 here. So if I'm in that situation, then eta concatenated with I will not describe an element of my tree, because it's, the starting point of the initial segment will not be a non-limit. Okay, so we're just going to cheat, and we're going to use this notation anyway. So notice, like, okay, what was the tree partial order? The tree partial order was inclusion of functions. This thing that I've written down here, eta concatenated with I, is still a function, right? It just doesn't start at the right place. It's a function that is no longer starting at a non-limit. So I can still compare elements of my tree T alpha to that function. I can ask, okay, which are the elements in my tree that contain this function? And so by abusive notation, we will use the tree partial order to compare elements of T alpha with eta concatenated with I, even in the edge case that eta concatenated with I is not an element of the tree. That's okay. Okay, so that makes sense. And then, so that was adding something at the top, right? Something above eta in the tree. Now I want to describe how to add something at the bottom. And for this, you're going to actually go from the alpha tree to the alpha plus 1 tree. So I need to, so to add something on top, I need to add one new thing at the beginning of my domain. Now, when I want to add something at bottom, I need to add a new element at the end of my domain. So that means passing from something that ends in alpha to something that ends in alpha plus 1. So if I have eta, which is in T alpha, then I concatenated with eta will be the tree in alpha plus 1 that defines the function on alpha to be I. So it extends the value by 1, adding alpha to the domain, and makes it have value I. Cool. And this note is just a recapitulation of what I was saying above, that you can still compare elements of the tree to eta concatenated with I, even if eta concatenated with I is not in the tree. Just thinking about how the tree partial order is defined, it's defined in terms of inclusion of functions. Okay. We have neighbors that have 2 corgis, and at about this time they walk by, and Shelby goes ballistic. I mean, I go ballistic too. They're very cute. Okay, so the point of these T alphas is to use them as an index model for a certain kind of indiscernible tree. That's what we're after. So let's recall the class of S-indiscernible trees that we were working with at the beginning. So S-indiscernible trees, as you recall, are this is when you have the index model that has the tree partial order, the binary meat function, the lexicographic order, and predicates for the levels of the tree. And if you recall from before, what we said was like, okay, P0 is like the level 0, P1 is level 1, P2 is level 2, and so on and so forth. And now we're going to have a level for every non-limit in alpha plus 1. And I'm going to interpret P beta to be those nodes, i.e. those functions whose domain begins at beta. So that identifies a level. Notice that there is something that switched here. I mean, so before the P0 named things that were below P1, which names things that are below P2, and the order has switched. But okay, it's not a big deal. You can still show that this is a perfectly well-defined class of structures, and its age is, its age restricted to any finite sublanguage is a Ramsey class, and so T alpha indexed indiscernibles will have the modeling property. So if we take a big collection of tuples indexed by T alpha, we can extract from them an S indiscernible tree, and that will have all the indiscernibility properties that we care about, provided that we don't mind that we only know that sort of things at the same level have the same type. Things that are sort of at different levels are identified by different predicates, so that their types might be different. Okay, so this works just like LS did, except we just added new predicates. And oh no, it seems like my screen has frozen. So let me stop sharing again. Okay, so now we're back, I hope. Yes, okay, good. So great. So I think the last piece of sort of general notation or terminology that I need to introduce is that of restriction. So imagine that I have some subset of the non-limits. Or actually, I should say non-limits of alpha plus, okay, non-limits of alpha for the time being, whatever. I want to say what it is to restrict T alpha to those levels. So I imagine W as being like a set of levels, and I want to restrict to just those levels and sort of look only at that part of the tree. So what does that mean? What that means is I look at functions in my tree whose domain starts at an element of W. Okay, so if I take the minimum of the domain, meaning the starting point of that in segment, that should be an element of W. And then outside of the elements of W, I am always 0. Okay, so let's just imagine what this looks like for a second. Let's suppose that W consists of 2 elements, like, so for example, let's suppose W is equal to 3 and 5. And we look at T over 2 W. What does that look like? Well, what that looks like is, oh no, I think it's lagging again. Okay, so this should be isomorphic to omega to the less than or equal to 2. Okay. Well, okay, I think omega to less than or equal to 2 minus the empty node. Why? Well, because, okay, what are the options for where your function ends? I mean, so what are the options for the end of the in segment? Or the beginning of the in segment? The beginning of the in segment can be either 3 or 5. Those are the 2 choices. Now, if you're defined at 3, and you're defined at 5, then you can choose any value to define your function at 3 and at 5. So that's like level 2 in the tree. You have sort of a choice for where to define 5 and where to define 3. On the other hand, if you're only defined at 5, then you just have countably many choices. That's like the first level in your tree. And those are the only two options, right? And you have to be defined at either the first in segment or the second in segment. And those are the only 2 degrees of freedom you have, because the way you're defined at any of the subsequent elements has to be 0. So you get omega to the less than or equal to 2 minus the empty node, because you don't actually have an empty function in this case, right? Yeah, so good. So that tells you that sort of like the number of levels that you're restricting to roughly tells you the structure of the tree. It's going to look something like, if the set has size n, then you can imagine that it's going to look like omega to the less than or equal to n minus the empty node. And it sort of tells you, okay, this is what these 2 nodes look like. So we're sort of zooming in on what happens there. Then perhaps you all remember this like Erdos-Rado fact, which we used to extract indiscernibles when we did simplicity theory. We were describing how you can construct Morley sequences in simple theories. And we said, okay, if you have a simple theory, you start with A independent with B, you'd like to have a Morley sequence starting with A, which is MB indiscernible. How do you do that? Well, you just iteratively apply extension a whole bunch of times. You produce an extremely long sequence, and then Erdos-Rado tells you that from that sequence, you can then produce an indiscernible sequence, which is not just locally based on the sequence that you constructed, but actually based on it. So any n-tuple in the indiscernible sequence that you produce realizes a type, actually the type of an n-tuple realized from the sequence that you started with. Whereas local basedness only says that any formula that's true of an n-tuple in the indiscernible sequence has to be satisfied by n-tuple from the original sequence. So it's a kind of upgrade from formula to type that Erdos-Rado gave you, and the cost of that was making the sequence very long. So there is a pretty straightforward modification of that proof, which we didn't do in this class, that tells you that you can do something very similar for large indiscernible trees. And so what is the exact claim? Well, I'm just going to give it in this case. But suppose you have a model of your theory T, and given that model, there's a cardinal. So the size of the cardinal only depends on the size of the model T. It actually doesn't depend on the model, but rather just its cardinality. But okay, this is good enough. There's a cardinal kappa such that if I have a collection of tuples indexed by T kappa, so remember this is like a tree of height kappa, consisting of functions defined on n segments of kappa that begin at non-limits and have finite support. So I have this really big tree of tuples, and I'm going to just assume that that's S indiscernible. So S indiscernibility distinguishes between the tuples indexed at different levels, right? However, what this says is I can find some other tree, B eta in T omega. So now I've gone from something indexed by something very big to something very short, indexed by T omega, which is S indiscernible over M, and has this additional property that somehow it doesn't matter which levels I look at, I always get the same thing. So one way of saying that precisely is whenever I take a finite set of levels, so whenever I look at some V, which is in omega to less than omega, so it's a finite set of levels, then there's some other finite set of levels from the original tree, so the non-limits of kappa, such that if I look at eta in T kappa restricted to nu prime, that has the same type over M as B eta in T omega restricted to nu. So what is that saying? That's saying that anytime I take an n-tuple of levels, then the type of the tree that I get by restricting to those levels realizes that, that type is also realized by an n-tuple of levels coming from the original tree. That's what that condition says. So this is like being based on the original tree. This is any type realized by an n-tuple of levels must be realized by an n-tuple of levels in the original tree. That's the first thing. And the second thing says that actually the types you get by moving from this n-tuple of levels and this n-tuple of levels, or this n-tuple of levels, in this new tree be omega, that type is always the same. It's like somehow indiscernible vertically as well. So precisely what that means is if I take two finite sets of levels which have the same size, and I restrict my tree first to the first set of levels and then to the second set of levels. So I restrict B eta to eta in T omega restricted to U, and then I restrict it to T omega restricted to U prime. So these are two different n-tuples of levels. Those two trees realize the same type. So S indiscernibility says a lot about like horizontal indiscernibility. For example, like if I take a sequence of cones, those will all have the same type. If I take children of a common node here and children of a common node here, these form like a mutually indiscernible array, that kind of thing. But it doesn't tell me anything about what happens when I move vertically in the tree. Like if I take something at this level and something at this level, they could have totally different types. So this condition upgrades that, and it says that okay, if I take something at this level and something at this level, they have to have the same type, because both of these things are in restrictions to like one level. Or if I take a restriction to these two levels and these two levels, I get the same thing. So that's like an upgrade from what S indiscernibility gives you. Cool. So this is like Erdős-Rado, but for the tree. Great. So now we're coming to the central definition, which is that of a Morley tree. So before we had Morley sequences, now we're going to upgrade that to some notion involving trees. How are we going to do it? Well, here's the key definition. We say that A eta in T alpha is spread out over M if whenever I take a node in my tree, which is not at the top, so the minimum of its domain is not 0. So it's something that isn't at the top of my tree. Then there's some global M-invariant type, which we're calling Q eta, extending the type of the cone above eta concatenated with 0. And eta concatenated with 0 makes sense because we weren't at the top. So that if I look at the sequence of cones, like eta concatenated with 0, eta concatenated with 1, eta concatenated with 2, so on and so forth, like as I'm concatenating with progressively increasing natural numbers, that sequence of cones is a Morley sequence in that type. And I shouldn't have said it this way. It shouldn't say in some global M-invariant type. It should say in Q eta. So in Q eta over M. Of course, if I didn't have this Q eta, then I could have said that it's a Morley sequence in some global M-invariant type. That's the key thing. So if I take a node and I look at the sequence of cones above it, that's a Morley sequence in some global M-invariant type. So we have this picture here. Here I have fixed some node eta right here, and I can concatenate with 0 or 1 or 2 or 3 or 4, so on and so forth. And I can look at all the nodes above those functions, eta concatenated with 1, eta concatenated with 2, and so on and so forth. And I want that to be a Morley sequence in some global M-invariant type. So this is saying something about the way I move horizontally through my tree. That's very generic. All right, now this looks strange, but it turns out that this is going to be a diversity condition on the tree. It's saying that your tree is very spread out. Okay, so that's hence the name, right? As you move horizontally through the tree, you're moving generically. So this cone is somehow very far away from this cone, which is very far away from this cone, because it's moving along Morley sequence. It's like filling up space. Okay, so now we come to the definition of Morley tree, which is just a tree that is somehow spread out and indiscernible. So what does it mean to be a Morley tree? A Morley tree over M is a tree that is first S indiscernible and spread out over M. So you're S indiscernible. So that says a lot about moving horizontally. So in particular, notice that like this spread out condition that we had said that like whenever I take a node that's not at the top, if I look at the sequence of cones above it, that's a Morley sequence in some M-invariant type. But being S indiscernible tells me that all paths have the same type. So it's enough actually to check that at the all zeros path. right? Like if I take something on the all zeros path and I look at the cone above it and the cone above it concatenated with one, it concatenated with two, and so on and so forth. If that is a Morley sequence in some global invariant type, then that will be true for any node in my tree. Just because of this fact that the tree is S-undiscernible, so I can move horizontally. But I'm also going to insist on being able to move vertically. And that's where we insist on this condition that comes from Eros-Rado that says that, okay, whenever I take two sets of levels that have the same size, then the restriction of my tree to the first set has the same type as my restriction of my tree to the second set. So this says that no matter where you look in the tree vertically, you always get the same answer. So one observation to make here is that, okay, if I just think about what happens along the all zeros path, this condition B, which is highlighted in green here, will say that that sequence, the all zeros path, the things indexed by the all zeros path, are an indiscernible sequence, right? Because, okay, what is the type of, say, the first three things in that sequence, the things indexed by the all zeros path? Well, that's contained in the type of the restriction of my tree to the levels 0, 1, 2. And I know that that's the same as the type of the restriction of my tree to say 6, 7, 8. And so that tells me that the type of, say, the 3 tuple of the sequence indexed by the all zeros path, the 3 tuple starting at 0, 1, 2 is going to have the same type as the piece indexed by like 6, 7, 8. And no matter which n tuple I take from the all zeros path, I'm always going to get the same type. That's encoded by this condition B. So that's really what we take from this. The main thing is that paths now through my tree are M indiscernible sequences in virtue of this condition B. And for us, that's like the key. That's the thing we care about. Because actually, at the end of the day, we don't care so much about the trees. The trees are somehow like a kind of scaffolding we build in order to construct a certain kind of sequence. And that sequence is going to be the kind of sequence that we need in order to witness Kim dividing, and as a consequence to prove symmetry. Okay, so how do we define the sequence then? So a tree Morley sequence is a path in a Morley tree. And that's it. So a sequence, AI, I less than omega, is a tree Morley sequence over M. Sometimes we call these TMSs for simplicity. So you have a tree Morley sequence over M. If there's some Morley tree over M, for which that sequence is the all zeros path. So recall zeta I is the identically zero function that starts at I. And so what I'm saying is if I have a Morley tree whose all zeros path corresponds to the sequence I'm given, then that means that the sequence is a Morley tree. Okay, now of course, in a Morley tree, the tree itself is S-indiscernible, so any two paths have the same type. So I could have said that there's some Morley tree and some path in that tree which corresponds to the sequence. Or I really could have said that it has the same EM type as something, because maybe I want to take it to be indexed by something other than omega, but at least this is a definition, right? This at least tells you how to do it when it's defined by omega. I want some Morley tree and some path in that tree that corresponds to my sequence. So the slogan is that tree Morley sequences are just paths in Morley trees. And what is a Morley tree? A Morley tree is an S-indiscernible and spread out tree, which has this additional indiscernibility condition that tells you that you can move vertically in the tree so that the paths are guaranteed to be indiscernible sequences. Okay, so that's the idea. And here I have a picture of the all zeros path in Morley tree, and I'm saying that, okay, A0 corresponds to A zeta 0, which sits at the top here, and then A1 corresponds to A zeta 1, which sits just below it, and A2 corresponds to A zeta 2, which sits just below it. And as I travel down this tree, I'm traveling up my indiscernible sequence. Okay, so that's the definition. Now, here is a key idea. So let's recall when we were studying simple theories, we defined Morley sequences. And how do you define a Morley sequence? Well, a Morley sequence over M in a simple theory is just defined to be a sequence I less than omega, which is M indiscernible and has the property that AI is independent with A less than I for every I. That's all it is. Now, when we define Kim independence, you could look at Kim Morley sequences. Okay, and what should a Kim Morley sequence be? A Kim Morley sequence should be just a sequence I less than omega, which is M indiscernible, and has the property that AI is now Kim independent with A less than I for every I. It's a sensible definition. Okay, so whether or not that is enough to do what we want to do with it, namely to prove symmetry, that's an interesting question. It's a complicated question. But one thing that we can observe at the moment is just that tree Morley sequences are Kim Morley sequences in that sense. So they are Kim Morley sequences. And it's not obvious, right? I mean, you do this funny construction of a tree, which has these weird conditions on cones, blah, blah, blah. I mean, why should that be a Morley sequence at all? But this will be a consequence of Kim's lemma, actually. So suppose we're in anisotropy 1, we're in an anisotropy 1 theory, and we have a tree Morley sequence. So I claim that not only is AI independent with A less than I over M in the sense of Kim independence, but actually, if I fix an I and I look at A greater than I, that's going to be independent with A less than or equal to I for every I less than omega. So actually, the whole end segment of my sequence is independent with any initial segment, which is in principle a bit stronger. Now, if you remember, in simple theories, this is also always true for Morley sequences, which we proved using base monotonicity and left transitivity. So you can sort of move things into the base and move them into the right by induction. And so it's always true in a Morley sequence that an end segment is independent with an initial segment. Here, it's less obvious, but let's see why this is true. So let's look at A eta in T omega, which is a Morley tree witnessing that our given sequence is a tree Morley sequence, right? So we were given a tree Morley sequence. That means that it is the all zeros path in some Morley tree. Let's call that tree A eta in T omega. Then if I'm given some J and I look at the initial segment, A less than or equal to J, that's contained in the cone above zeta J. Remember that our all zeros path goes down. So if I look at the things which are indexed less than or equal to J, that's like the things in the tree that are above zeta J. So these elements, A less than or equal to J, are, it's like a subtuple of the tuple that enumerates the cone above zeta J. So I've drawn this in this picture here. So if you fix this J, which we have here, like right here, then the thing in blue will be like A less than or equal to J, because that corresponds to A sub zeta less than or equal to J. And that's contained, of course, in this cone, this first cone that I see, because it's like the all zeros path, the part of the all zeros path that's in that cone. Now, as I move horizontally and I look at the sequence of cones, that itself is an M invariant Morley sequence. And by S indiscernibility, that is indiscernible not just over M, but over M and the green bit, the in segment of my sequence. So I said that here. So if I look at this sequence of cones, A greater than or equal to zeta sub J plus 1 concatenated with K as K varies, that's M A zeta greater than J indiscernible, which is just a fancy way of saying that this sequence of magenta cones is indiscernible over the model together with this green bit that we have here in this picture. Okay, and then what does that mean? Well, that means that the end segment has to be independent with the initial segment. Why? Well, because I have exhibited for you a Morley sequence in some M-invariant type in the parameter, which is indiscernible over the object. And what does that mean? That means that they have to be independent by Kim's lemma. Because if there was some formula in the type of a greater than j, with parameters coming from a less than or equal to j, which Kim divided, then that would have to be inconsistent along any Morley sequence in the type. That's what Kim's lemma says. But that is incompatible with that sequence being indiscernible over a greater than j. So this is one of the uses of Kim's lemma. In order to show that two things are independent, it suffices to simply exhibit a Morley sequence in the parameter which is indiscernible over the object. So that does it. That says that at the very least, what we're looking at is a Morley sequence. So okay, that was like a lot of setup. Now, what we're going to do next time is we will prove that tree Morley sequences exist. And that is something we haven't justified yet, right? We've defined them, and we have this, a lot of terminology and machinery that we had to develop just to sort of talk about the index sets. And we haven't really yet justified why we're looking at these weird index sets, but that will be an artifact of the way that the proof goes. So what we're going to do next time is we will prove that tree Morley sequences exist, and from that we will be able to deduce symmetry. So that's going to be what comes next. So next class period, we will pick up from here, proving the existence of tree Morley sequences, concluding symmetry, and that will be the end of the story for NSOP1. And then we will move on to NTP1, and then that's it. That's it for the class. So we're nearing the end. All right, so I will stop there. Are there any questions? Okay, so one thing I wanted to say is I was sort of thinking about this class and like writing the notes, and I realized that I've sort of neglected to talk about examples. Like I think we haven't discussed so many examples of like, okay, this is simple, this is stable. I mean, we did talk about like the random graph and DLO a bit, but we haven't really talked about examples of these newer tree properties that we're caring about. Like what's an example of something which is NTP2 but not simple? What's the example of something which is NSOP1 but not simple? So next time, I suspect that it won't take the full hour to talk about symmetry. So I'd like to spend some time talking about some of the examples also. And I don't know how much depth we'll go into, because oftentimes to prove that something is NSOP1 or NTP1 or NTP2, whatever, you have to like first prove quantifier elimination, and then you do inspection on the quantifiers. And it's like something that's best done by yourself. And it's not really fun to listen to someone explain. But anyway, I mean, I think we'll at some point before the class ends, we should definitely sort of sit down and look at really basic combinatorial examples, so you can get a feel for like, okay, this is what it looks like when a structure has these properties or doesn't. So don't let me forget to do that. And yeah, I finished the NTP2 section of the notes, so be on the lookout for those. They'll be posted sometime today. And most of the NSOP1 and NTP1 notes are also already written, but somehow in other files. So it's just a matter of copying and pasting them in, and then we'll be done with that. I don't know if anyone ever looked at these notes, but they're there. So avail, take advantage of them if anything is unclear. And I know that some things have been unclear. So cool. I will see you all bright and early on Friday.